Yeah. Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. We have the pleasure of having today Adele Marshall. She is a professor of statistics at the School of Mathematics and Physics at the Queen's University Belfast. She is also the director of the Virtual Institute for Data Intensive Research and the director of the Mathematics Academy. Her research interest includes survival analysis, Bayesian modeling, data mining, Markov modeling, and stochastic models. The research applications in which she's working range from a strong foundation of healthcare research and medical statistics and operational research to infrastructure modeling and flow modeling. Her research has appeared in leading journals such as European Journal of Operational Research, Pattern Recognition, Healthcare Management Science, etc., etc. And she has received funding both nationally and internationally. So we are very pleased of having you today, Adele. For the audience, as you know, if you have very, very urgent questions, please put them in the chat and I will read them for the speaker. And if not, we will take the questions at the end. The floor is yours, and thank you again for coming.
Thank you, Dolores, and good afternoon, everyone. Thank you all for attending today. As Dolores has said, my research spans a number of different areas, and you'll see from my title for today, I've listed data analytics, machine learning, and statistics, and of course, operational research is important to me as well. And one of the messages, I guess, from my presentation today is that it's not that I'm going to talk about how each of these techniques are perceived and how people understand the meaning of each area. It's more my perception and how I felt that some people fit nice cleanly in one area or perceive each area as very distinctly different. From my own research and from my experience, I have seen that it spans across all areas, and I tend to use the data analytics approaches, machine learning, operational research, and statistics interchangeably as and when I need, which is why today I'm talking about hybrid models, where I bring different techniques together as really like a toolbox of whenever I need them. And the applications I'm going to refer to today are healthcare applications, and that's really just one strong area of my interests, my research interests that I've been working on for the past 20 years plus. So without further ado, I'm going to start by talking about survival analysis. So survival analysis, as you know, it's a well-known technique. It's a traditional approach that's been used for decades in statistical modeling and healthcare modeling, particularly in healthcare and medical research. You will hear of survival analysis. And my talk today is really looking at more traditional techniques and how they have changed over the years, as I suppose, the need for data and the different types of data that we're experiencing now, and different challenges we're experiencing, how our approaches have changed, how we can still use some of those very important traditional techniques, but we also can explore lots of new ideas as well and new developments. So survival analysis it's a group of statistical methods used to model time until an event occurs, and that time could be in healthcare, it could be the time it takes someone to recover from a disease, or it could be in manufacturing, the time it takes a component to wear out, to need replaced. There's a wide range of analysis and approaches or applications, from commerce, from actuarial science, all the way through, that would use the applications of survival analysis. But we define survival analysis using a survivor function, which we denote as S of t, which is just really the probability of an individual surviving longer than a particular time, little t. and we say that's the probability of capital T being greater than little t. And the figure I'm showing is just some examples of what a survivor function looks like. So it's just, if it's a probability, its values can range from 0 to 1, or in this case from 1 to 0, because we're looking at the beginning of a study, everybody will not have experienced the event. They'll be starting the study, so the probability of surviving past that point will be 1. But as the study progresses, people start to experience the event, and then as time goes on, then the probability of others experiencing the event reduces, so it eventually diminishes to 0, and as a result you tend to have a skewed distribution, which is quite typical of survival analysis. Associated with the survival function is a hazard function, and I'm not going to go into definitions today, but it's the instantaneous failure rate, if you like, is how it's defined. And associated with that, then you'll have a probability density function, and you can work out cumulative functions from that as well. So the three functions are interchangeable, and if you have, there's a nice way of moving and transitioning between the expressions of formula to be able to derive one from the other two. So it means that you can use survival analysis to model lots of different types of data. Some of the examples of data that I've used to date are modelling patients in hospital, and particularly the elderly patients in hospital who are seen to use a lot of resources and spend a lot of time in hospital because they generally have multi-comorbidities and lots of other complications, and less straightforward than maybe some younger patients. And you can see just two examples of data sets. The one on the left is a data set that was collected for 20 years between mid-1960s to the 80s, and the one on the right is one that was collected in the 1990s. Although they are from decades apart, you can see that the shapes still are quite similar. You have that skewed nature, and even just getting a simple descriptive statistic like your mean and your median can show that skewness in our data, because we can see how different they are for the data set on the right hand side for the clinics data set. So these are examples of data sets I've used in the past. I'll talk about some others that I've used more recently, but they're typical survival data. One of the things with survival analysis, and there's lots of different approaches in survival analysis, it allows us to model time until an event occurs. But it also allows us to look at some covariates and see, well, covariates are just what the other information that we know, how it interrelates or influences and explains some of the survival. So we talk about covariates, and there's a technique, well-known, well-published approach that's used widely, known as Cox proportional hazards model, which allows you to incorporate other covariates into your model of survival to derive their influence on the survival and the effect that they have. And you can also calculate a hazard ratio, which looks at the hazard rate between the impact of a variable on a set of baseline individuals or experimental units, whatever you're modeling. Another thing of survival analysis is a censored feature that it allows you to represent data up until the time and point it's censored. So you can use left and right censored data where maybe the event isn't observed during the study. But just focus on, we're going to look at more at the covariates for now, because that was something that whenever I started modeling and using survival analysis and looked at covariates using Cox proportional hazards, I wanted to see if I could explain more. First of all, try and see if I could learn the distribution that this is from. So the distribution we're seeing at the moment, you can see it's not normal, obviously, it's skewed. You may have some ideas. You can see maybe part of an exponential there. Maybe it's a mixture of exponentials. And that's really how I started looking at other distributions to see how we could best fit this type of data to a statistical distribution. So that brought me into looking at Coxian phase type distributions. So Coxian phase type distributions, they allow us to model time until the event occurs, or model the time, and they model time until absorption. So in our case, that might be the patient leaving hospital, and it can be modeled using a finite state Markov chain or process in continuous time. And we can calculate rates of flow of movement between one state in the Markov process to the next state. And we have parameters to derive that using lambda I and mu I. Coxian phase type distribution is different to a phase type distribution in that the phases are ordered. And by doing that, it means that those parameters, those lambda I and that mu I that we wish to derive or use to represent our data, that there's fewer of those that we have to estimate, because obviously the easier it is to fit our model, the better. And the diagram I have here is just a sketch of a phase type distribution where you can see the parameters lambda I and mu I. So if, for instance, if this were patients in hospital, it would be like patients arrive into hospital all in phase 1, and then they can spend a period of time in phase 1 before they get absorbed, where it might be that they leave hospital and they would do so at a rate of mu 1. Or else they may continue their stay into their next phase in the hospital, which they would do at a rate of lambda 1. And they would continue through the process, either leaving at a later rate of mu I or continuing in their stage of care in the hospital at a rate of lambda I until they're finally all absorbed. And associated with that, then, those lambda I and mu I we can represent in a transition matrix, which we call Q. And using the transition matrix, then we can calculate the probability density function of this distribution with P, E, Q, T, Q, where little p and q are vectors, which I've represented there. So that is a mechanism which allows our distribution that we can use and fit to survival data to represent the survival data. And the benefit with using this distribution is that it allows us to represent the process in different stages, which in some cases have shown to be very representative of the real life scenario. Obviously, there are drawbacks as well, and we'll talk about those in a moment. So this is just an example where I fitted that second data set, and you can see the lines actually might look quite faint on your slides. You've got a red and green line with the different phases in the Coxian fit. And the process that I would go through when I'm fitting a Coxian is I would formulate the likelihood function, and I would fit it using the maximum likelihood, with our unknown parameters being lambda I and mu I. And I would start with fitting one phase to the distribution, which is just a single exponential distribution. And then I would iteratively add in additional phases. So then I would fit two phase, and I would compare the first phase fit with the second phase fit using just comparing the log likelihoods. I'd also look at Bayesian information criteria and other measures to check the fitting process. And I would repeat that process, fitting a third phase, fitting a fourth phase, and so on, each time checking whether there's any significant difference, any significant improvement from adding that additional phase into the model, until I get a stage where there is no significant improvement by adding in an additional phase. At that point, I would suggest that that would be the optimal fit, or the optimal number of phases for the Coxian phase type distribution to represent that particular data set. Obviously, I don't do this by hand, and we've generally been using MATLAB and R, and some SAS actually. We've used SAS in the past as well, but mainly MATLAB and R to do the fitting process, where it's an iterative fitting process. And as part of that process as well, for the optimization, we use NeEDS for to help with the fitting process as well. So that's just one example of using the Coxian fits. As I said before, one of the disadvantages at the moment is that we've just got a continuous distribution that we've been able to fit to. But ideally, what we would like to do is add in additional characteristics. So we'd like to add in other features about the data and see if we can represent them in a way that can be incorporated into the survival distribution. And this is where then I worked on a discrete conditional phase type model, which is where I developed the model for the continuous survival distribution as before, using the Coxian distribution. But instead of trying to use a Cox proportional hazards model, which is very different, I wanted to see if my covariates could link to the different stages in the survival time. So I wanted the covariates to be incorporated in some way into the Coxian phase type model. So I did this in two parts, and this is where we start to see my interest in combining different techniques and hybrid models. So I had a Coxian distribution, which I referred to as a process component that represents the survival distribution, as we talked about before. And then I had a conditional component, which I had all the interrelated discrete variables. In fact, you could use continuous as well, but I mainly used discrete variables if just depending on what data was available. And from that, form some kind of network or interrelationship of those other descriptive variables or covariates, and use them then to derive or influence the survival time in the Coxian phase type distribution. First example I used was using a Bayesian network. So I had fitted a Bayesian network alongside the Coxian phase type distribution. So just this is a visual of what it would look like. So we had a conditional component of what the Bayesian network of the interrelated variables. And then on the other side, we have this Bayesian network and all of its variables influencing each other, then feeding into the process component, which is the Coxian phase type distribution. So this meant that every time we were fitting and optimizing the fit of the Bayesian network, we also had to optimize and be in parallel fitting the Coxian phase type distribution. So we would have had a likelihood function of two components really in the likelihood function. So you have the conditional probability, the product of the conditional probability of the causal nodes in that network, and they're conditioned on their parent nodes in the network, raised to the power of the number of each units in each of those different sub levels of the node. And that was times the product then, the likelihood function for the probability density function for the Coxian phase type distribution. Again, this was fitted using MATLAB in this particular case. And here's just one example. I've kept examples reasonably simple in these earlier pieces of work just for description purposes. So this example is back to that data set I'd talked about originally, collected in the 1990s. And here we had the Bayesian network interrelating variables. And from that, we could see that there was only two key variables actually that were the ones influencing the patient length of stay, the Coxian phase type distribution, and that was the Bartel grade, which is a level of patient dependency on others to do everyday activities, and their destination. So this model wasn't for prediction, it was more for just explaining what impacts the length of stay. And so these are the two variables that then we could from that derive fitted Coxian phase type distributions for the different Bartel grade scores and the destinations. And that was for St George's Hospital in London. Separately then, another piece of work, I'm sorry, it's catching up with me. Another piece of work is we fitted a distribution to look at modeling the time of patients in hospital based on other information about them, and this was for hip fracture patients in a hospital in Belfast in Northern Ireland, and there was lots of different variables interrelated. We used a special type of Bayesian network called a block recursive model for this, where we had some variables that had associations and then the others that had more direct influence on them. And from this we could see that the delay for the patient to get the treatment, the surgery impacted on the length of stay that they had afterwards. And again, Bartel score, that level of dependency on the patient influenced how long they spent in hospital. So the dependency of the patient on others, I should say, not of themselves. So it's dependency of the patients on others to do everyday activity. And this seemed quite reasonable, that if a patient got delayed in their surgery, well, then it would suggest their condition was getting worse. And maybe then by the time they had the surgery, they needed longer recovery. And likewise, the Bartel score coming up as being significant. Well, it's a measure of how able someone is to cope independently. And if you're not coping well independently and need a lot of support, then it's likely that you'll need more time in hospital to recover before you can be discharged home or rehabilitated back home in your home environment. So that's just two examples of where we used the discrete conditional phase type model. There is an added complexity here, because once we're fitting all of these covariates and how they interrelate in a network, in a Bayesian network, and in parallel you're fitting each type of Coxian formation you can get from the subgroups, if you like, of patient, it becomes very complex and very hard to fit. And as time progressed, we looked at other different types of ways of doing this as well. This is just how the results will look. So once the Bayesian network appears, you will have your probabilities of the patients falling in each of the different subcategories, and then you can derive the number of fitted Coxian phase type distributions to each of the levels of the patient. So for instance, a patient that was delayed only a day, and if they were independent, a three-phase Coxian distribution fitted well. However, if you had a patient who was delayed greater than 3 days and were independent, the number of phases to explain their stay in hospital, it got more complicated and tended to be longer, and therefore we needed 5 phases to explain the time they spent in hospital afterwards. So associated with each of those, you would have the probability density function and survivor function for the patients in each of those different subgroups and their corresponding Coxian phase type distribution. As I said earlier, that gets quite complicated as you add more and more variables in, and so you have more and more variables that are influencing. We only had 2 variables, Bartel score and our other score on, dependency score and our delay score. So we looked at other different approaches and found, in majority of these cases, we've applied all of these different techniques in different scenarios. And this is where I find that it really does depend on your data and the scenario that you're in as to which of these approaches. There's not one magic answer that one model will work. Some have nice features, some are more explainable, which is important especially in the healthcare area. Others are less so, but they all have their own characteristics. Some will give a better prediction and a better fit. So we did use these models. We've used, for instance, logistic regression and naive Bayes classifier and different forms of where we've worked with the covariates first and then fed that into the Coxian phase type distribution. So we're really then having 2 different models coming together into a hybrid model, and they're only linked by the variables that are seen to be the significant ones in patient length of stay. And as a result, the fitting process is actually a lot less intense. Another thing we looked at was, is there any way in modeling the Coxian phase type distribution that we can actually identify differences in the covariates according to what phase the absorption takes place? And from that, then we can calculate a probability of absorption from the kth phase of the Coxian phase type distribution, and from that work out the boundary values for length of stay in each of those categories. and then consider the patients in each of those categories and their corresponding covariates individually or separate to each of the other phases. An example of where we used this was what work I've collaborated with colleagues, Laura Boyle, who's in Queen's University of Belfast, and Mark McKay, who is in the University of Adelaide in Australia. And this is where we'd looked at a data set. There's 120,000 records in this data set. It was a brand new hospital at that time, opened in 2017. And it was the world's most expensive hospital at that stage. And they had dashboards looking at the emergency department, and red was negative, it was bad, which suggested that they referred to as red hot or white hot, meaning that it was in a bad state and under a lot of pressure. So we had looked at the data to see if there's any way we could help explain to the hospital managers what was happening by looking at the data and the covariates. And we started by fitting Coxian phase type distributions to this again to see whether we can determine any behaviours in the length of time the patients were waiting in the emergency department. We could see that there were two distinct forms and shapes. So the patients who were being admitted tended to have a very different distribution waiting time in the emergency department than the patients who were being discharged. Again, this might seem reasonable, straightforward, because you would expect that those maybe getting a bed in hospital may need to wait longer to get that bed. So there were some features that we had, that seemed reasonable. However, sometimes whenever the time clock stopped whenever, and it went into the next stage in the process whenever they were given the decision to admit. So it's really only up until the decision to admit rather than waiting until they had a bed themselves. So this is typical of the skewed distribution, fitting a Coxian distribution to that. The parameter estimates are there at the bottom with the associated log likelihood and the Bayesian information criteria value. And we had iteratively went through all the number of phases 1, 2, 3, 4, 5, 6, 7 and deemed that there was no significant improvement after the fit of the 6th phase type distribution. And that's the point we terminated the fitting procedure. And you can see that it gives you a good fit. And likewise, you can do the same. That was for the discharge patients. You can do the same for the admission patients. And they had a fit of a 6-phase fit, interestingly, as well, although theirs was shifted to the right compared to the others. So the parameter estimates were very different. And associated with that, then we could apply the calculation of the equation that I showed a few moments ago, where we worked out the probability of being in each of the different phases, and then from that examine closely the proportion, the characteristics, and this is just using one particular variable just as a means of an illustration of, for that first stage, you can see the different breakdown of the patients. And so that was then used to help inform hospital management in terms of how to allocate their beds and management beds and resources and staff as well. But I want to really turn my attention to two other case studies, and it again links into survival analysis, and it's more recent. It's in the last year, 18 months. And these two case studies I'm going to talk about are focused on some of the COVID modelling that I've been involved in. The first is actually with collaborators in Ontario Tech University. I'm an adjunct professor in Ontario Tech, and the work is in collaboration with a colleague in Queen's, Alex, and a colleague in Ontario Tech, Carolyn. And the work we were doing here is looking at the delays experienced in reporting COVID-19 and reporting confirmed positive cases. And we did that using survival models. So this is a very was very current and very important at the time. It's over a year ago now since we reported on this, but at the time you can see how the traditional survival analysis techniques that were used in the earlier and much earlier than what I've done work can still be applied and can still add value. And in the next example, I'll show one where we looked at compartmental models and then moved to stochastic models, and we'll talk about those in a moment. So just to give you a summary, this was looking at Canada's COVID-19 journey, and in particular we were looking in the Ontario region. At that particular time, there were a total number of COVID-19 positive cases in Canada of 1.4 million. So that was in June 21. And that had increased even since I prepared these slides, which was a few months later. And most of the cases were found to be in Ontario area and Quebec, and those would be quite highly populated areas, so it wouldn't seem unreasonable to a certain extent. In the bottom right-hand corner, you can see the COVID-19 confirmed positive cases, the total number per day during the period. So you can see that there were a number of different peaks in the distribution as a lot of countries experienced at the time. Sorry, my slide stopped for a moment. One of the things that was of interest at the time to everybody was NPIs, which were non-pharmaceutical interventions. And non-pharmaceutical interventions happened, a lot of governments decided on these. And they could have included, in this particular case, for instance, what we're looking at in Ontario was the closure of schools. So in September the 9th, 2020, Ontario schools closed. And then there was new public health guidelines that whenever schools were to return, that any child exhibiting any symptoms from the list of symptoms that were defined wouldn't be allowed to return to school unless they were completely symptom-free and had a negative COVID-19 test. So there was a suggestion that this put a significant load on testing and caused delays in processing. And it was also important to note that timely detection at that stage, whenever there were a lot less of the population vaccinated or immune, there was a timely detection and isolation of positive cases was extremely important. At the same time, there was a government public inquiry taking place in Victoria governments in Australia, and they had suggested that for contact tracing systems to be considered effective, that you should really have 90% of your tests and reported positive cases reported within 24 hours. And that positive cases, close contacts, should also be notified within 48 hours. We didn't have information on the close contacts, but we did have the reporting data, which is what we wished to model and see whether there was any impact on some of the MPIs and the decision that all children returning to school had to have a negative COVID test, and whether that impacted on the service for everybody else. Sorry?
We are okay. Yeah.
Okay. Sorry, I heard a noise. So we had publicly available data on positive COVID-19 cases in Ontario, and this is available from Ontario's Ministry of Health and Long-Term Care webpage and Public Health Unit. So for each positive case, we had just some information. We had the estimated date of the symptom onset of the disease, the exact dates from when their specimen was collected and processed in the lab, and when the lab notified the Public Health Unit about the positive case. So here's where we didn't just use the traditional survival analysis, but we actually are looking at multiple different time points. So some people may refer to it as process mining, where we're taking the data and we're mining the process using, in our case, survival analysis for each of the different stages in that process. So I don't need to describe survival analysis. I talked briefly about it earlier. One of the approaches within survival analysis, which I briefly mentioned earlier, is Kaplan-Meier. And Kaplan-Meier allows you to estimate a survivor function. And that's the expression there for the estimation of the survivor function. So again, these are well-known traditional techniques that we're going to look at. And the idea was we were modeling the delays in COVID-19 information reporting process. And we did that for a year, from the 1st of April 2020 to the 31st of March 2021. We also wanted to look at the Cox proportional hazards model, and from that we can derive a hazard rate, and you can see the hazard rate that we can consider. So we had certain variables that we could consider, such as the month whenever the patient was reporting, the age of the patient, and the outcome of them whenever they were going to hospital. So these are just some aspects that we wanted, the only variables really that we had for covariates. So we didn't have a vast amount of covariates, but we wanted to estimate their coefficients and see whether they were having any impact on the length of time or the processing time. So here's where we have applied we've first of all just plotted some survival times. So we have the average reporting, we have the timeline along the top, and you can see there the time it takes. So the average or mean overall reporting delays between different stages of the COVID-19 process, and I have listed those in colour. So we have various from the onset of the disease until someone has went and got a test, then from the test to whenever the lab has got the result, the lab then reporting that result to the public health unit. So these are all labelled and they're all colour-coded there for you to see along the bottom. You can see there then that the average response delay in days, and particularly you can see there that the time it takes from symptom onset to reporting to the public health unit, so that whole process in generally significantly decreases. Initially it was 6 days in April 2020, or 6.26 days, but by March 21 it was 3.5 days. So people got better at reporting it, and the system became more efficient. It wasn't new over time. It was able to reduce. The largest contributing factors then to reporting times with delays with the in-between stages, you can see between the stage of symptom onset to specimen collection. So there's still was some delay in people coming forward to get their test, and again that can be for a number of different reasons. And likewise from the specimen collection until the processing in the lab, and again because initially I guess there was a lot of elderly, and the elderly patients may not be as mobile, or there are multiple different reasons again why their specimen collection may not have been processed in the lab as quickly. And we applied the Kaplan-Meier model to the data, and here's an example where we've applied it. So you can see the probability that the delay in information from the stage we're looking at SCD to CRD, which is the reporting stage, to the public health unit. You can see that the vertical dashed line represents what was reported in the Australian report, that you should have at least 90% of the test results back within 1 day. We actually allowed here less than 1 day, so we led up to 2 days, but less than 2 days, not including 2 days. And you can see there in this particular case, this 90% of cases reported within 2 hours is not the case. It only really happens for this data set for the blue vertical line for February and for March of 2021, so the most recent months. And we also could see that there was a lot of variation between months, and there were some months more extreme or worse than others. So we had April, September, December of 2020, January, February, March of 2021. So we wanted to have a closer look at those, and we're able to have some further findings from that. So we can see that the largest delay occurred in September 2020 for the specimen to the test report. The test report to the public health unit showed that in September 2020 was performing as good as the best performing months. So the test report to the public health unit, didn't seem to be a delay there, and there were fewer confirmed cases in September 2020, suggesting that policy change has impacted on the processing times. And then likewise we have from the 6% chance of delay in the information between stages at least 2 days at February. So the cutoff point of being less than 2 days or should be reported 90% within 1 day. Well, we're seeing 94% of they're processed within a day, well, less than 2 days. So it's improved over time, and at the very end of the data extraction and model that we were doing, that the February-March Ontario performance was at least 90% processed within 24 hours. Okay. There are other findings from this, but I'm just conscious of our time. So I wanted just to skip on to really the main findings from all of this. The approach really illustrated, using the publicly available data, that we could apply our survival methodology, and it allowed us to have some useful insights into the modelling process and also where the delays were and whether changes in the policy, like the change in children, all having to be negative tested, whether that has an impact. And we did that using standard survival techniques like Kaplan-Meier and Cox proportional hazards, but we did it over multiple different time points within a process, so a bit more like process mining. The second case study that I wanted to talk briefly about is work that I've done in collaboration with, as part of the COVID-19 modelling group in Northern Ireland. And this is again an area where we start off with, what models do you choose? You're thinking of survival models, you're thinking of compartmental models, and what actually happened and the model that we arrived with at the end. And this work is in collaboration with my colleague at Queen's, Alex. So the challenge in this case was to develop an approach that could capture the disease dynamics of COVID-19 for the whole population of Northern Ireland. And I'm sure a lot of you have looked and seen a lot of other presentations similar to this already. We wanted to identify what were the key events driving the epidemic and get some kind of accurate estimation of the daily COVID-19 cases. And we were interested in this because we were being asked to see whether we can provide some insight through our models that could inform government decisions on non-pharmaceutical interventions, whether to introduce them, whether to relax them, what was the best stage or mix to use. Northern Ireland, in case you're not aware, is part of the United Kingdom. It has 1.8 million population, so seeing probably quite a small population to a lot of other countries. And the white larger circle in this map is of Belfast, which is capital and where a lot of the population would be. There would be a lot of other rural areas within Northern Ireland as well. So there's a mix of some big cities and then some other rural areas. We talked about looking at compartmental models, where you have your equation-based model and your theoretical framework for developing and describing the disease dynamics. And there was a lot of work already taking place in that area. and we were looking at other types of models to see whether we can complement what was being done already through compartmental models, and really wanted a more stochastic approach that was relying on the variability of the data. So we actually turned our attention to agent-based models, and as they are more stochastic in nature, and gives you a micro level view, and you're simulating from the bottom up to the macro level. So if you like, the compartmental model was like a top down or macro, and agent based allowed us to look at the individuals. So it's back to the survival, where you start with the individuals and you're trying to build the distribution around that. Most of you are aware, I imagine, of agent-based models. They're computer-based simulations, and they have a mix of different individual entities, which we call agents, and those individual agents are capable of working in an autonomic environment. They interact with each other in the simulated environment, and we can define some micro rules that describe how the agents should behave, and then try to simulate that situation and that environment, and then capture what happens at the macro level, and whether we can map that into some kind of realistic description of a real world system. So what we were interested in, look at the behavior of the agents combined with the transmission pattern and disease progression, and see whether it looks at the emerging population dynamics, how the disease is evolving. But one of the disadvantages of the agent-based model is that it's very costly to run in terms of time and power. If you're looking at each individual member of our population is 1.8 million, and I'm sure a lot of other countries have larger populations. Something to help direct and give these micro rules some meaning was we wanted to see, we could see from the shape of the number of daily confirmed COVID-19 cases that there were peaks and troughs, and we had different runs, if you like, and we wanted to see was there any way we can mimic the behavior of, or in the model of, the agents, which leads to one of those peaks, or which actually can reduce one of those peaks. So you can see there was sudden changes in the structure, there was these jumps and drops, it seemed quite volatile, and we actually used change point detection to help us with that, to try and identify where there was more statistically significant changes in the distribution, and underlie that with what was happening at the time in reality, and link it back actually to whether there were any non-pharmaceutical interventions, NPIs, taking place at that time that could have influenced it. So how did we meet our challenge? So we developed a model called CPABM. And this is really using, again, a hybrid model where we have the change point detection embedded into an agent-based model. And we calibrated it, and using lots of reported information from the literature, and also what data we had for Northern Ireland and the UK at the time as well. We applied it to Northern Ireland population, and we were able to successfully capture the patterns in the COVID-19 infection dynamics over 2 of the waves of the pandemic. And from that, we were able to quantify the effects of the NPI, in particular the national lockdowns and mask wearing. And we also then were able to use our model to further extend to suggest whether, for instance, other interventions such as closing schools at different periods over the holiday, over the Easter break or Christmas break, is necessary. So it's a combination of change point detection and agent-based modelling, and we wanted to make sure that it was realistically simulating the infection spread in the population and being able to quantify the NPIs that were introduced. So we had 2 components. This time we had a change point component, which identified the different waves and the peaks along the way. And then we had the agent-based component, which had the different states of the disease and the transfer and movement of patients from one state or agents' behaviour from one state to the other. The change point model could identify and picked out, and these colour bands represent different stages. One's the national lockdown, one's a local lockdown, one's wearing masks, and one's where there was no intervention at all. So from the change point, we got a good indication of the time points, the ticks in the agent-based model of when behaviour changed, and there we applied a different set of rules or micro rules for that period of time in our model. Our agents represented, we had 1.8 million or just over 1.89 for each agent representing one member of the population. And we had different infection status. We had, which I'll show you in the next slide. And we had one cell where you could have multiple agents in a cell, and whenever an agent moved from one cell to the other, they inherited the status of that cell they moved to. So we had lots of different cells or states. We had shielded at the time, where clinically vulnerable and individuals aged over 80 were shielded. We had those that susceptible, the rest of the population. We had those that were exposed with preclinical, clinical, subclinical, and recovered. And the dashed lines there indicate the interactions between the agents where the transmission of the infection could occur. So how did the IBM work? We had an iterative process of simulation. We implemented a series of discrete steps, which in the agent-based modelling we call ticks, and each tick represented a day. So we simulated each day, and we simulated this for over 200 days. And we looked at the baseline relative infectiousness for each type. So that was some of the input parameters we had, with the number of agents at each state at the beginning of the simulation, with the mean daily contacts in each segment between change points, which is again something that we had derived, and with the probability of the exposed agents developing subclinical infection at the end of the incubation period. So lots of input variables and the variations attributed to additional behavioural effects. So we had a behavioural effects distribution underlying it as well. We used a package called NetLogo, and we coded all of this up. I didn't decide to do a simulation live just in case there were any issues, but this was simulated for 216 days. And Dolores, please do keep me right of time, because I think we're probably nearly there.
Yes, but we can take a couple more minutes. Yeah, it's very interesting.
Okay, I'm nearly finished. So
yes,
I'll not go into this in too much detail. If anybody is interested, this work has been published in Pattern Recognition, and I'd be very happy to talk to anyone who's interested to learn more or hear a more detailed description of this. But all of these little boxes along the left-hand side are the different parameters for our model that we had either got from previously published work or other surveys where we had daily contacts of the population surveyed. We had susceptibility. Some of those we measured, as I said, those were input parameters. Then we had these different color-coded boxes representing those that were at risk, those exposed, preclinical, subclinical, and those that were recovered at the end here. And we simulated it, and then we're able to determine from the agents. This reported the daily number of clinical cases. We had it per age distribution as well, just for description purposes. And we also, you can see there, our R-squared value, for instance, is 0.97 of the fit for this model. So this was able to represent the dynamics of the disease quite well. Our outputs were that we were able to estimate daily cases, and we used this to evaluate the effectiveness of the MPIs against the estimated values for a number of different scenarios against true observed data. So we did this to help confirm our models, and then we could use this for tracking and for future MPIs. So it also implicitly captured the number of agents in each cell at the beginning, and it could track agent interactions. And we were able to use this then to inform the COVID-19 modelling group, quantify the effects of the MPIs. Wearing masks was one we could see very clearly had made a significant impact, and estimating the role also of the subclinical patients. You could see that it was successfully estimated, and also looking at the long-term effect over 2 waves. Most models could only look at one at a time. And this is just one example where we'd been doing we extended the work of Metz et al., where we were able to look at a longer period of time for mask effectiveness. I'll not go into any more detail on that. I'll just really conclude that it was used to predict future scenarios such as return to schools before and after Easter, and to inform decisions and policy making in Northern Ireland. Final remarks really is just, which are very broad. We started talking about hybrid approaches. In that last example, we'd used change point analysis, we'd used agent-based models, we had a genetic algorithm running to make our models more efficient. We'd fitted multiple statistical distributions. So we actually had a marriage of multiple different areas of approaches coming together, and they can be very effective. The key thing to remember when you're building your models is to think about their impact and really how can they be applied. So making sure that you can find a way that they can be applied, and that you understand your data, and really understand if there's issues with the data, how much confidence you place on your data, making the model reproducible, and also always keeping a broader knowledge of what else is out there and open to other approaches, because you never know when you may need to use them. Okay, thank you very much, and Dolores, I'll hand back to you. Thank you.
Yes, thank you very much, Adele. I love the final remarks that you made because they are very meaningful to all of us. I open the floor for questions. Is there any question from the audience? So we have a question from Sureya, yeah. And Jason is going to give the rights.
Hello, hello from Istanbul, from Turkey. Thanks a lot for this interesting talk. We actually listened with my students. I'm in the lecture now, and it coincides with my lecture hour in machine learning. It was really interesting. I have 2 questions. The first one is related with the hybrid methods. I'm studying on ensemble learning, so I'm curious about how you integrate these techniques. Did you do some aggregation using voting, or you take output of one component and use that as an input to another method, or how you did it? And the last question is about this, the last part of your talk related with agent-based modeling. I just felt intuitively relation with the game theory to find the best parameters, best decision, the optimal way to guide people to find the best scenario, finding the equilibrium like Nash equilibrium points using game theory. So I'm not in this field too much. I use neuroscience data in healthcare, and also it just came up to my mind. If those models can fit into this EEG signals, signaling data, can it be used in this Markov chain? I think it can be used. The first models that you presented.
Yeah.
Thanks.
Yeah. Okay, thank you, and welcome to your class. Yes, the first question, I've actually done it both ways, depending on the scenario that I'm looking at. In some cases, it's been where I've taken one component, one model, and the results of it have fed nicely into another model. So it's easier, it's much less trouble, and it's less computational if they are independent to a certain level, and it's only connected by a few dependent variables. Others, I've had to actually unpick and derive the equation that will allow me to fit it all together at the same time. And that's where the complexity comes in. For instance, your game theory could be helpful there. For the agent-based model, yes, we used genetic algorithms, but game theory could have been used. I'm sure there are a lot of other, and even different genetic algorithms we could have used. At the time, we were under pressure, and it was waiting. There were different departments waiting for our decision. So we were trying to do it as quick as possible, but there's lots of other ways I think we could explore it, and certainly if anyone was interested in that, it would be a nice extension of the work. For the neuroscience, for the application, yes, I believe you can use the Markov process to mimic the different stages and look at it for ECG as well. There is some work that we're looking at the moment so it's early work, but so I haven't reported in any results on it yet, but certainly I would be interested to explore that, and it's something where some of my collaborators could potentially have ECG values as well that we will be modeling in the near future. So happy to talk offline about that if you're interested.
Yeah, I am actually working on these EEG-based measurements recordings to understand the obesity actually before and after the diet. So I'm in the phase of writing a project. So we may discuss later on. Maybe I can send you the email, so we may collaborate.
Perfect. Yes.
Yeah.
Thank you.
Thank you.
Dolores, I cannot hear you.
Can you hear me good?
Yeah, I can hear you now.
Yeah. So thank you very much for coming today, Adele. And to the audience, we will see each other on December the 5th.
Okay, thank you very much.
Thank you very much. It was very interesting talking.